Hi, let's talk about the derivative. I have a graph of a function here, and I'd like to find the derivative of the point at x equals 3. So I have the graph of a function, y equals f of x, and I'd like to find the derivative, which means I'd like to find the slope of the point at 3. I'd like to figure out how can I find the slope of that tangent line? Now, until we have the derivative, we don't have any good tools to do that. So what we want to do is we're going to imagine a second point. We'll calculate the slope of the line connecting our original point and the second point. Now clearly this isn't the derivative. It's the slope of a secant line. But I can use it to approximate the slope of the derivative. At our first point, has an x value of 3 and a y value of the function at 3, f of 3. Our second point is at some unknown point, we'll call it x, because the x-coordinate is x, we don't know the y value, but we'll write f of 3. The slope of the secant line has a value delta y over delta x which is given by f of x minus f of 3 divided by x minus 3. This is the slope of the secant line. If I'm interested in finding the slope of the tangent line, I need to imagine that that second point gets closer and closer and closer to the first point, and the limit gives me the slope of my tangent line. And that's the derivative. The derivative is the limit of a slope where the second point moves to the first point. That's all a derivative is. Let's take a look at some examples. All right, to illustrate taking a derivative, here's our first example. We think of the function y equals x squared. We want to find the slope at x equals 3, so that's the slope of the tangent line. In our picture, we have the tangent line of x equals 3 shown in the blue line. This line is the tangent line. If I want to find the slope, what I need to do is I need to imagine a second point. I will call this second point at a point x, f of x. And our first point is at the point 3, f of 3. Now, for our particular example, we know the formula for our function, f of x equals x squared. And so f of 3 equals 9. I can now create a formula for the slope of the secant line. The secant line has a slope f of x minus f of 3 over x minus 3. Using the formula that we have, that's x squared minus 9 all over x minus 3. This would correspond to the slope of a secant line, which I attempt to draw in red. The slope of the tangent line is the limit slope is defined as the derivative at x equals 3. That's the limit as our second point gets closer and closer to the first point of our slope of our secant line. So let's visualize this. Here's a movie. As that second point gets closer and closer to the first point, you should notice that the red line, our secant line, starts to look very much like the slope of our tangent line. Okay. If I want to actually find that slope, my task is to find that limit. To evaluate the limit, we use algebra. For our example, x squared minus 9 factors. So let's rewrite our limit as x goes to 3 of x squared minus 9 over x minus 3. We take a limit of our new formula where we factor it, x plus 3, x minus 3, all over x minus 3. Because we have common factors, the x minus 3's cancel, and what we find is the slope of our tangent line is to calculate the limit of x plus 3. Well, this is a nice formula because I can actually plug 3 into that one. 3 plus 3 equals 6. Notice that as soon as I evaluated the limit and replaced the x by a 3, I stop writing the limit. The limit is there to remind me I need to take a limit as x goes to 3. Once I do, I stop writing the limit. And so we found it. The slope of our tangent line is 6. For our second example, we'll look at the square root function. Let's find the slope of the tangent line of the square root function at x equals 4. So we start by thinking about, what if we had 2 points? One point is going to be at x equals 4. Using our formula, we can find the value for y. That's the square root of 4, or the number 2. So on our graph, that will be the point 4, 2. For our second point, we use a variable. The x value we'll just leave as x, and the y value we'll use the formula, square root of x. So our second point is going to be at the unspecified point, x, square root of x. The slope of the secant line, which is shown in red, uses the standard slope formula. Change in y over change in x is the value of our function minus the value of our point divided by the change in the x values. So for this example, it's the square root of x minus the square root of 4, or 2, divided by x minus 4. And that corresponds to the slope of the red line. The slope of the tangent line is the derivative. So our derivative, dy dx, evaluated at the point 4, imagines that this second point moves closer and closer to the first point, so that the red secant line looks more and more like the blue tangent line. We represent that in calculus by saying we're taking a limit as that second point x approaches the point 4. We're computing the limit of a particular quantity, the slope, which is given by the square root of x minus 2 over x minus 4. The limit we've written down represents the derivative of the square root function at x equals 4. To find the value of that limit, we need to do algebra, but the limit itself represents that derivative. In order to do algebra, we need to rewrite that formula so that we can cancel out the x minus 4. Notice right now, if we plugged x equals 4 in, if I were to take the square root of 4, I get 2. 2 minus 2 is 0. And if I plug in x equals 4, 4 minus 4 is 0, I get 0 over 0. That's not defined. And so my limit is indeterminate. I need to rewrite it in a new form. The limit as x approaches 4 of the square root of x minus 2 over x minus 4 can be calculated using a conjugate, which means I take the square root of x minus 2 and I change it to the square root of x plus 2. And we don't want to change the values, so I can only multiply by 1. And this algebra allows us to rewrite the top using FOIL, or distributing everything out. Square root of x times the square root of x is x. The outer terms are 2 square roots of x. The inner terms are negative 2 roots of x. They cancel, and I get x minus 4 divided by x minus 4 times square root of x plus 2. My limit has x approaching 4. X minus 4 is a common factor, and so I can find that my limit is found by taking a limit as x goes to 4 of 1 over the square root of x plus 2. Well, this is no longer a problem. I can plug 4 in. 1 over the square root of 4, that's 2, plus 2, I get a final answer. The slope of my tangent line, represented by a derivative, at the point 4 is equal to 1 over 2 plus 2, which is 1/4. That's the derivative.